This is a video lecture for Math 181 for Monday, April 27th. And the topic today is using integrals to calculate a volume of a solid object. And the basic idea behind this is we're going to take our solid object and we're going to cut it up into a series of very thin slabs. And then we're going to calculate the volume of each of those slabs, add all those volumes up, and that's how we'll obtain the volume of our solid object. And this is, to make a silly analogy, this is very similar to having a loaf of bread. Here's a loaf of bread. So this loaf has a certain volume. Well, we're going to divide this volume up into a series of slices. We're going to calculate the volume of each slice, add up all those slices to get the volume of the solid object. This is very similar to the approach we used with areas, the areas under a curve, where we approximated the area under a curve by dividing it up into a series of rectangles. We calculated the area of each rectangle. We added up all those rectangles to get an approximate area under the curve. And in the limit, as the number of rectangles went to infinity, that approximation became exact. So similarly, in this case, we're going to take the limit as the number of our slabs goes to infinity, and that will give us the exact area of our solid object. To get a little more mathematical about this, each slab will have an area A of x sub I. And the x sub I just indicates where along the x-axis we're slicing that particular slab exists in the overall solid object. Each slab will have a thickness delta x, and therefore the volume of each slab will be, if you think about a very thin slab, the volume of that slab is simply the cross-sectional area of that slab times the thickness. Again, here the thickness is very small, right? So the volume will just be the area times the thickness. And then what we're going to do is sum up the volumes of all these slabs. So the overall volume of our solid object will be approximately equal to the sum from I equals 1 to n of the volume of each slab. Okay? And then we're going to take a limit as n goes to infinity. And as the number of slabs goes to infinity, this volume, the volume of the solid object, will become exactly the limit as n goes to infinity of the sum from I equals 1 to n of the volume of each slab. Okay. This is very similar to what we did when we calculated areas under a curve and when we derived our integral formula, the definite integral. And this, in fact, is the definite integral. This is the definite integral. If you guys remember, if we had f of x sub I, that was the definite integral of f of x. Well, here, instead of f of x sub I, we have a of x sub I. So this turns into a definite integral of a of x. So the area is a function of x, where you are along the x-axis. And then here, the delta x has turned into a dx. So dx is our new very thin thickness of each slab. And so now we have an integral from a to b, a definite integral from a to b of a of x times dx. This is the theory behind calculating the volume of solid objects. You know, if you have a very simple solid object, such as a cube, you know, we all know how to calculate the volume of that. But if you have a more complicated solid object, how do you calculate that volume? We have to use calculus and the process of integration to calculate those volumes. In this is the first part of this video. In parts 2 and 3, and possibly 4, I think I'll do two other parts. We're going to do example problems and show you how to use this formula to calculate the volumes of specific solid objects.